Okay, we're going to take a look at just the intro to basic polar coordinates. I think what we need is just some help and some polar. So this is just general understanding of polar, all the how to convert them, how to graph. This will not include limicons and roses. I'll put that in a separate video. So if you can just check this out, this ought to help most of us. I'm going to try and make this full size for you guys. Let's do it. Go enter full screen so you don't have to see all the other stuff. And we're good to go. This has more information. I'm going to load this file up for you guys to look at too. This is a much better description of what polar versus rectangular coordinates really look like. So there's some nice descriptions in here of things you want to know how to do. So if you can handle reading some of that, that would be awesome. In the meantime, I'm just going to highlight some key pieces. The thing is you guys know that if we do XY coordinate graphing, we usually go left, right and left a certain amount, that's our X, and then we go up and down, that's our Y, to get to a point. With polar, we look at this differently, where we swing to a certain angle, and then we extend a radius of a set amount to land on that same point. And the crazy thing, what allows you to have, in polar coordinates, you can have basically an infinite number of representations of that one point. Because how you get to that angle, there's a lot of ways to do it, right? You can do negative angles to land me there. I can go around multiple times. I can do coterminal angles of some kind. The other option that we have with polar is a radius that's negative. So I can actually pick an angle that's facing the exact opposite direction over here, but my radius, while I'm facing this direction here, we'll call it, let's see, southwest. If I do a negative radius of a certain amount, in this case 1, 2, 3, 4, that would land me on that particular spot. So there's just a lot of representations that happen when you're dealing with polar. Down below there's some things that are important to know. The polar axis is that x-axis. The rings represent various radii from the pole, the origin. And r, when I say radius r, is listed first, but really the independent variable, like the one that we want to think of first, you want to do the angle first. So when you're talking about a particular point, you want to say what's the angle that'll get you pointing in that direction first, and then do the radius that corresponds to it. The reason that's really important is what if I'm doing my angle is facing the opposite direction, then that would make the dependent radius would be a negative value. You'd have to go backward a negative radius to land on that point. So I'm thinking of this as kind of a review with some more details, and so if you want more help on that, you're going to want to run me down. The basics, though, are all written up in here, so we've got that part. I'm going to go down below. Important note I just said to you, too, is that the independent variable is theta. That's the one we think of first, the input variable. We would think of our domain of polar graphs being the possible thetas. The output, or dependent variable, is r, and that means our range of possible values will be the radii, the smallest and the biggest the radius could possibly be. Okay, so down to this picture here. These are polar coordinates, so if I'm going to graph these in any particular way, so I'll go right on this, all of these, if I graph them, you start with the angle. So the first one, 3 pi over 4, you're going to go, all right, pi over 4 to 1 pi over, 3 pi over 4, got it, facing this way. You go the angle in that direction. And then what you do is you go out the said radius, and it's a circular radius, remember? So when I think of 2, it's somewhere on that circle. So for ours, it's right there, your diagonal step. So here's 2 on the x and y axis, and then what you do is you want to go out, though. It's kind of in between those. You want to measure carefully. So here's, you kind of make an arc between 2 and 2 on the 2 axes there, and that's where my 2 is. That's roughing it out, and that's totally fine if you're just doing a sketch. Then, if you're going to do the next couple, and I'll just do these relatively quickly, always go negative pi over 6. You deal with your angle first. It'll be facing this direction. Okay, so, and then 4 would be a radius of 4 would be going out 4 steps. If you had the rings going like I had up in that picture above, that's really helpful. If not, I usually just do 4 and 4 on both axes and then kind of swing an arc over and say, yep, yeah, right about there. That'll do it. Part C here, another one, negative 3 pi over 2, so I'm facing all the way over here. And then I do my 3 halves, which is 1 1/2 is my radius, and so somewhere between 1 and 2, I'm going to squeeze a nice little point in there, and we're good to go. Okay, negative radii, so these are going to be really important, D and E, because I'm going to go to a particular angle, 5 pi over 3. So I'm going to count my pi over 3's, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. I'm facing this direction, but I'm going a negative 3 radius, And so while I'm facing down there, let's say to the southeast, I actually want to go in my radius the opposite direction, -3. So it's actually going to go somewhere up here in this direction. Okay, so I'm facing that 5 pi over 3, but what I'm going to do for my radius is go the opposite direction, 3 spaces. Same thing with this next one, -pi is my radius. So I go to 0 degrees, which is facing to the right, so there's 0 degrees. And then -pi would mean to go the other direction, 3.14, so it's just somewhere out here, a little past 3, there'd be my point. So those are points. They are coordinate points. You could graph them in the XY coordinate system. It is possible to do that, and that's actually what we'll look at next, is converting between those. All right, let's go to the next piece. Here's how, if you're dealing with polar versus rectangular, this is a really nice diagram that'll help you kind of get the sense of what's going on. If you look at this, there's one rectangular coordinate we can do for any given point. So I got it up here. P is x comma y. Radius and theta and a polar representation, like I said, you could do the angle in a number of ways. There's an infinite number of possibilities. So just keep that in mind. And then this little system that I set up here for graphing that single point, point xy or r theta, this right triangle here is really key, because if you notice that right triangle, if I dissect it a little bit, you're going to notice all these little formulas that represent that situation down below are our keys to converting back and forth between rectangular and polar. And we do that. They both are valid representation systems. So sometimes we want to convert to rectangular and vice versa. Sometimes we want to convert to polar. So these formulas here are really important. In this case, they're broken up to kind of show you when I'm going polar to rectangular, I want to use x equals r cosine of theta. And when I'm doing the other way around, rectangular to polar, then I'm tending to use these formulas over on the right-hand side. They're all related. They come from the same right triangle connecting to a particular coordinate point. So this hopefully gets you back on track if you lost your way somewhere along the way. I'm going to bump this up a little bit. This is a polar coordinate that I've got number 2 here, 2a. I want to convert this, so what I have is an r, and I have a theta, and I can take that and use that information to find, hey, the xy system is just -5 cosine of my theta is going to give me, and this is -4 pi over 3, right? And then -5 sine of theta, that's going to give me my x or my y coordinate. That's it. That's all it takes to get to. You notice up here, that's the conversion formulas I'm using from polar to rectangular. Is just I can get x and I can get y from r cosine of theta and r sine of theta respectively. It all comes from, if you look at this particular situation, the cosine of theta in this triangle would be adjacent over hypotenuse, x over r. And if I multiply both sides by r, I get this formula, r cosine, of theta is equal to x. And we can do the same thing for y and sine of theta. So that's where that's coming from. Those are the formulas we use to convert. Then you go to your unit circle to figure these out. -5 times 4 pi over 3, we're going to go exact, right? We want to have our unit circle memorized. If you don't, you need to find a way to do that. Talk to me or find a resource of your own. But -4 pi over 3, so I go on there, all right, pi over 3. I'm going the negative direction, 2 pi over 3, 3. -4 pi over 3. Bam, that's my direction. My radius is -5 as I do that. But I'm thinking this is unit circle. I just want to know what's the cosine at -4 pi over 3. And if you know your unit circle really well, it's -1/2. And the sine at that same angle is going to be positive radical 3 over 2. And we can simplify those as needed. So what do we get here? That's 5/2, comma, -5. Here we go, radical 3 over 2, and voila, that's our coordinate point. Those will match. If you plot this point, I can make a better bracket than that, this point, and I plot this point using their respective systems, they'll land in the same place. Okay, moving right along, we got another one to do, and I'll just make some quick work out of it. 4 cosine of -5 pi over 6, comma 4 sine of -5 pi over 6. Real slick, and that's just, again, unit circle business. If I'm going around and I pick out what -5 pi over 6 is, faces me that direction. If I do cosine, that should be negative radical 3 over 2. And my sine of that value should be -1/2 times 4. Whoops, that is a lot of -1/2 just put in there, so I can make better work of that. So we get 2 radical 3 comma -2. Those are our coordinate points. Okay, example 3. Convert the following rectangular to 4 different equivalent polar pieces. Now polar, these are x and y values. Remember, this is x and y in rectangular mode. So for polar, though, we want to turn that r. It comes from r. We've got this formula up top here. Go revisit these real fast again. R squared equals x squared plus y squared. That's going to allow us to get r. We want to know the conversion of this is also plus or minus the square root of x squared plus y squared. And then we know the tangent of theta is going to be y over x, which means theta that we're actually looking for is going to be the inverse tangent of y over x. So ultimately we take inverse tangent to get that value for theta. Okay, so these are really what we end up using. The plus or minus is important for the radius because we do incorporate, we want to look at both the positive and negative radii representations of a given point. We'll talk more about that in a minute. So r squared would be the -2 squared plus 2 squared. And we get r, whoops, I don't need a squared in there, do I? Sorry about that. Get that out of there. Yeah, let's make that an r. That's r, and that should be a plus or minus. So r is plus or minus the square root of 4 plus 4, which is the square root of 8. And you guys you can simplify that, which is plus or minus 2 radical 2. Okay, that's our radius that we're going to use. We can put that in if we're just going to talk conversion here. So we're doing plus or minus 2 radical 2. Let's go with, we'll do both. We'll do a 2 radical 2. And then we'll do a point with a -2 radical 2. I might not do 3 like the instructions say, just to save us some time. But notice what this means. A positive radius and a negative radius, they're going to require a different angle to make that work. So theta is going to come from, as I said before, the inverse tangent of y over x. As I showed you up top, so 2 over -2, which is the same thing as the inverse tangent of -1. And you want to know your unit circle for that one. So if I go to the unit circle and I talk about tangent, tangent is 1 at these two corners and -1 here and here. So that's what, 3 pi over 4 and 7 pi over 4 is when tangent is -1. And I think for whatever reason I wrote a funny number in there. I think I wrote 0. But inverse tangent of -1, it happens at, in our picture, 3 pi over 4 and 7 pi over 4 within 2 pi. We can do a lot of representations of that with coterminal angles, but those are 2 good ones. The point I'm actually trying to plot, -2, 2, you can't lose track of what the actual point is. This -2, 2 point, if I actually plot it somewhere, you guys know where that is, right? -2, 2, let's do a quick graph, is here. Left 2, up 2. So my polar coordinate is supposed to represent the same thing. Well, what I'm going to get is by some angle I need to be pointing at this direction and go out a particular radius, which we know is 2 radical 2. The angle that's going to make that work, where this radius is positive, is going to be our 1, 2, 3 pi over 4 angle. So if I'm facing 3 pi over 4, my radius should be 2 radical 2 to land at the same point as -2, 2 in the rectangular system. If my radius is -2 radical 2, that means I need to be facing that 7 pi over 4 angle, because then it would allow, then I would go backwards to make that point that's on the left-hand side there. So we're going to do another video here. That's the part 1, just converting.